Hi. In my previous video, we did talk about leveraging artificial intelligence in life sciences. This video is going to be a little bit more of a deep dive in terms of leveraging artificial intelligence in life sciences. Most of you are already aware of this, so I won't spend a whole lot of time explaining this slide. This essentially pictorially depicts the relationship between artificial intelligence, machine learning, and deep learning. We will also talk about neural networks later on in this discussion, which is a part of deep learning. Let's talk about use of artificial intelligence in medicine. You can broadly classify this into three areas. One is interpreting medical history, second is diagnosis, and third is drug discovery. So when we talk about interpreting medical history and diagnosis, to some extent, they are looked at it in a combined fashion. We will talk about that a little later. And of course, then there is use of AI algorithms when it comes to drug molecules discovery, and then also use of artificial intelligence in clinical trials when it comes to patient recruitment. And as you see out there, there is significant potential in terms of use of AI in the healthcare industry. Some estimates put it at around $150 billion by 2025. When we talk about leveraging artificial intelligence, data sets are key components when it comes to leveraging AI. So let's look at some of the data sets that are available today. This is just a partial subset. There is much more that's available. When we look at public domain data, you have PubMed, which is research publications that are out there, and companies frequently write algorithms to go after that data to find out as much as they can on research that has already happened. Then we have gene expression omnibus, which is essentially disease gene expression data. This genomic data that is available out there in public domain. We also have connectivity map. Connectivity map is essentially gene expression data pre and post drug treatment of certain sample drug molecules that are available. Now, the pre and post drug treatment expression data can be compared to see which genes are differentially expressed. So between these data sets, one can even leverage these data sets and write algorithms to figure out which existing approved molecules, drug molecules, can be repurposed to treat other diseases. And there have been success stories. In fact, in one particular case, they found that they could repurpose an existing drug for a particular strain of Ebola, which is a great victory because just by using artificial intelligence algorithms, a treatment pathway was found. This is more of a pictorial view of what we just now discussed in terms of leveraging gene expression omnibus data that essentially has disease expression genomic data and the connectivity map, which has gene expression data before and after drug treatment on cultured cell, and then leverage these data sets and use algorithms and find potential repurposed candidates of drugs that are already approved and out there in the marketplace. Before we talk about leveraging artificial intelligence in diagnosis, let's talk about a particular type of AI algorithm. This is a deep learning neural network called the convolutional neural network, or the CNN. The CNN is usually used to solve what we call as the image classification problem. In this example, we have an X as the image coming in. To keep it simple, we are taking an X in this example as the image coming into the neural network. Now, this is a pixel representation of what the X might look like, which are essentially these black boxes. And when you convert them into a numerical problem, here you see it is represented by the plus ones for the solid black boxes and -1s for the blank boxes. Now, once you have this converted into what we call as neurons, or a matrix of +1s and -1s, then what the neural network basically does is applies what we call as the filter. The filter is essentially used to simplify the matrix structure. Now here you have a 3 by 3 matrix structure. Leveraging the filter, what we can do is to convert that into a 2 by 2 matrix structure. Here's how we do it. You see the +1, -1, -1, and +1 here. Now, what we can do is take these, each of these individual cells, and apply against these 4 cells, represented by the red circle here. Now, when you do that in a sum product manner, essentially the +1 multiplied by the +1 gives you a +1. Similarly, a -1 multiplied by a -1 gives you a +1. And if you continue the same thing and add all that up, you will essentially end up with a 4. And when you do a similar math on using these 4 numbers and apply that against the 4 cells in the matrix represented by the green circle, you will come up with a -4. And you keep doing the same with the orange circle, or the 4 cells represented within the orange circle, and also the yellow circle, you come up with this matrix. Now, when you then what you do is you typically apply a function called rectified linear units, which is essentially a function wherein you take these -4s, any negative number, and flatten them out with a 0. So what is left is basically these 2 4s, which can be represented by the solid black line that we see here. Now, you do the same thing with a different type of a filter on this neurons, and you will come up with this matrix. So essentially what you've done is you've taken a 3 by 3 matrix, converted that into 2 by 2 matrix, and kind of simplified it. Ultimately, this will get converted into what we call as a fully connected layer, which is nothing but a string of numbers through application of filters, and then you apply a probability to kind of read what the number is. And the way you do that is initially when you create this neural network, you feed labeled data into this. So by repeated process of learning, it kind of determines the probability of any input number without the label being an X, or for example a 0. So this is a very simple explanation of what a convolutional neural network is. As the image gets complex, the way the neural network actually reads it by applying filter and simplifying it, that's the whole idea here. In short, what a convolutional neural network does is based on past label data that is fed into a CNN. When you feed in a new image, it is able to look at the features of the image and conclude what the image represents. This is another example of a convolutional neural network. It is exactly the same, except that here we have a circle instead of an X. And as we see here, the same exact process is kind of applied, wherein there is this string of numbers, or a matrix of numbers in a 3 by 3 matrix in this particular case, and then a filter is applied, and then the whole process is kind of simplified to a string of numbers in what we call as a fully connected layer. As we mentioned earlier, initially, once this algorithm is written, labeled image data is fed in, so that the neural network kind of learns through this process in terms of identifying features of the image. Subsequently, when an unlabeled image is fed in, it is able to go through the same exact process and look at the features through repeated application of filters based on the complexity of the image, and then come up with the fully connected layer and apply the probability based on previous learnings, and then determine what the image actually represents. Now, this is a very simple explanation of what or a very basic explanation of what a CNN actually is. There are many videos available on YouTube that actually explains this in a lot more clarity. The idea here just being, to kind of give a high-level view of what a CNN is, and then talk about the application of CNN from an image classification perspective, and use it to talk about use cases in medical diagnosis. This slide is just the summary of what we talked about. Essentially, as we discussed, CNNs are used to solve image classification problem, and the model needs to be trained with labeled data. I will not touch upon areas like gradient descent because the whole discussion can get very complex when we talk about that. And we would leave it at this high level and now talk about use cases when it comes to medical diagnosis. Now let's look at some of the use cases leveraging CNN, the convolutional neural network. Macular degeneration is a situation wherein the central portion of the retina called macula degenerates. Macular edema is a case wherein there is liquid formation in the macula. Both of these are leading causes of loss of vision. And in a particular case study, there were about 200,000 eye scans that were used to train and detect macular degeneration and macular edema. And this was compared to the diagnosis from physicians, and CNN showed 95% accuracy. Not only just did it identify the macular degeneration and macular edema in 95% of the cases, but it also went one step ahead in terms of making some treatment recommendation in terms of referring a particular case further to a physician. So this is a great example of how artificial intelligence, and in this particular case, a convolutional neural network, can be leveraged from a medical diagnosis standpoint, building in a significant amount of accuracy and also timeliness in detection. So imagine, leveraging these technologies in many countries that do not have that many number of trained ophthalmologists. This actually does a first level parsing in terms of figuring out whether a patient should be referred to an ophthalmologist. This is another example of how a convolutional neural network was used to diagnose malignant melanomas. So the magnified images or the scans were input into the CNN, and then CNN was able to separate out malignant melanomas from the benign moles. Now, these results were actually compared to the diagnosis of about 50 dermatologists from around the globe, and surprisingly, CNN performed better. Dermatologists, of course, increased their performance slightly when additional clinical information was provided, yet the CNN results were stunning in terms of identification of the malignant moles. So this is another example of how CNN can be used in diagnosis, and not just save time in the whole diagnostic process. Also, this could be a very cost-effective and more accurate as these kind of neural networks mature down the line. This is another interesting use case wherein conversational AI was used to kind of determine whether a person had Alzheimer's by evaluating or analyzing the speech of an individual and to look for use of pronouns over nouns and then to evaluate whether there is a cognitive decline and diagnose Alzheimer's. This, of course, uses a different type of algorithm and not a CNN. We spoke about protein binding in my previous video, wherein we spoke about leveraging artificial intelligence in drug discovery. So especially with the genomic sequencing, we discussed about how a gene expresses itself by releasing protein or RNA. And for a molecule to be a potential solution for a disease, first it has to bind to the protein. So a molecule that is a candidate or a potential candidate should effectively bind to the related disease protein. Now, this is called binding affinity. We will be looking at some more use cases, especially some of the newer algorithms in AI that are being experimented from a drug discovery perspective. So I thought it might be a good idea to kind of recap on what we discussed with regard to protein binding. Now let's talk about one more type of algorithm or a neural network that is being experimented and a long way to go. However, it's showing some promise. Now this is called a generative adversarial network. Which has this kind of an algorithm has two parts. One is a generator and one is a discriminator. To kind of explain this in layman terms, think of this as a counterfeiter appraiser scenario, wherein a counterfeiter will create, say, a painting that will look like the original, and the appraiser has to determine whether it is an original or not. And send feedback to the counterfeiter. At some point in time, the counterfeiter will, based on all the feedback received, may be able to come up with a painting that looks exactly like the original, and the discriminator is no longer able to discriminate between the fake and the original. Now, this is a very interesting concept because there is a generating algorithm in this generative adversarial network wherein it takes features and then converts them into images, and the images are fed to a discriminator. The discriminator is nothing but a simple convolutional neural network that we spoke about, which takes an image, converts it back into the features, and then determines what the image is. Now, especially with millions of molecular structures available, and when it comes to trying to find that one particular molecular structure that can bind to a specific disease protein, you can think of how a generator can create molecular structures based on features required, and then the discriminator or the CNN can actually determine whether there's an actual compound or molecule that actually matches with the desired molecular structure for effective protein binding. Now, these kind of networks, or the generative adversarial network in this case, are not very easy to work with, and the strides that the AI community has made, though noteworthy, it's a long way away. But given the fact that it's able to generate structures and images, and then use a discriminator in the fashion that it's being used, is a very, very interesting way of looking at leveraging artificial intelligence in areas like drug discovery. This slide shows what we already discussed in a bit more detail. Like I mentioned earlier, the required features are fed into the generator from a molecular structure perspective for a required protein binding. and then those molecular structures that are generated by the generator is fed into the discriminator. The discriminator also receives labeled data of real molecular structures. This way, it can compare the required features with the features in the real molecular structures and come up with potential candidates that can potentially bind to the disease protein. This is another example of using machine learning algorithms and interpreting medical records and looking for medical conditions to help the diagnosis. In this particular case, an hospital built a system to diagnose sepsis by leveraging records of past patients who had sepsis and using it in conjunction with patient records of current patients to determine whether the patients had sepsis. And in this particular scenario, they were able to actually determine whether a patient had sepsis 12 hours earlier than traditional methods. And in the case of sepsis, 12 hours can distinguish between a life and death circumstance. So this is a classic case of leveraging technology, artificial intelligence, machine learning to save lives. We did talk about leveraging artificial intelligence for patient recruitment for clinical trials. Now that one has the genomic sequencing data that can be combined with EHR and EMR data, which is the electronic health records, and also information coming in from social media sources like patient portals and all of that, and come up with algorithms to kind of determine a potential list of recruits. This kind of speeds up the process and also reduces cost of clinical trials significantly.